Welcome to the code walkthrough for CoDel in BlueStore. Ismail is going to take us through his pull request and design and experiments around that. So Ismail, do you want to take it away?
Sure. Let me just share my screen. So for today, before going through the code, I thought it's good to go over the problem and the architecture of the solution, and then go through the code. And I have some experimental result to basically go through. So let's start with the problem. So the problem we try to solve is that basically in most storage systems, we have front end and back end. The back end is specialized to store the blocks and everything on the disk, and the front end is the higher level of the storage. For example, in Ceph, we have OST as front end and BlueStore as back end. But the problem is that if the backend queue is very huge, like in BlueStore, it will accept all of the requests quickly and basically shovel them all to the backend. So, and this is good for the throughput because it's maximize the utilization of the disk and the resources, and the throughput will be basically maximum. But it would be really problematic for the schedulability, because in the front end, basically, if we want to schedule the requests, we need to have a few requests in the queue to be able to schedule between them. By having all of the requests to the backend, we are having this problem of schedulability on the front end. On the other hand, if we do the backward and keep most of the requests in the front end and a few in the backend, we are favoring the schedulability, but we are basically ruining the throughput, basically, because the backend will starve. The project is basically trying to have a smart and intelligent admissions control in between to control how much request and the transaction should be submitted to the backend, and keep a balance between the schedulability and the throughput by some parameters. So the very related and similar algorithm that already exists is CoDel. Basically, is used to to solve the buffer bloat problem in the networks. Buffer bloat is really similar to our problem when a network buffer too much data to the downstream. So the CoDel algorithm is very simple. Basically, it has a parameter called target delay. So it measures the queuing delay of request and compare the minimum queuing delay with that threshold. If the basically this minimum latency delay basically violates this rule, is going to initiate a packet loss, and basically it's going to decrease the size of the TCP window. And by doing this, it controls the packet flow in the system. We try to implement the similar idea in the Ceph. So this is the final form of our algorithm. Basically, we have two different loops. There is a high frequency loop which tries to minimize the latency by controlling the number of basically the number and the amount of requests into the backend by using a target latency parameter. And a lower frequency loop that tries to optimize that target parameters based on the throughput of the system and the latency, to be able to create and keep a trade-off between the throughput and the latency in the system. So basically, if I zoom here. So the fast loop is basically our CoDel algorithm that tries to control the BlueStore throttle budget by using a parameter called target latency. it measured the minimum latency of the whole BlueStore, and then compare it to that target latency. If there is a violation, it's going to shrink the throttle maximum size. And the slow loop tries to optimize these target parameters based on the throughput and to keep the basically trade-off between the throughput and the latency. So this is the basically the algorithm for the fast loop. It's really similar to the original CoDel, but we had a little few tweaks. It measured the whole latency of the BlueStore to generalize this problem to different backend as well. We just keep the minimum latency of the transactions and the requests and compare it to the target latency parameter. If it's bigger than the threshold, we are going to decrease the throttle size of the BlueStore. Otherwise, we are increasing the throttle size. It's basically a basic Newton optimization. For the the slow loop to basically to keep the trade-off between throughput and latency, we have a new parameter called target slope, or the trade-off between throughput and latency. If we have the basically the graph or the curve of the throughput latency, we can argue that the slope of this curve show the trade-off between throughput and latency. In this curve, basically, if we have a few requests to the backend, we are going to have a low latency but lower throughput as well. But if we send more requests to the backend and fill the backend, we are going to increase the latency and the throughput. But at some point, the throughput will reach the maximum capacity of the system. So it's not going to increase that much, but the latency will also will keep increasing since all of the requests is spending their time inside the BlueStore and they're just waiting there. The idea behind the slow loop was to monitor this basically the slope of this curve and find the target latency that is optimal for that workload. So this is the overall view of the slow loop. This loop monitors the throughput of the BlueStore and keep it inside the throughput latency model. It's just a point, the target latency and the throughput, and we keep those points, basically a history of those points inside the memory, and we are going to age it out after it sometimes. So we are keeping a fixed number of the points here. And then we use this throughput latency point to basically estimate the curve of this throughput latency. So it's really, so the throughput latency curve can be estimated by a logarithmic function. So we estimated this function with the logarithmic regression. And after that, we can find the best throughput, the best target latency for the workload based on the target slope parameters. So this target slope is basically a controlling parameters that controls and give the basically user and the operation teams control over the trade-off between throughput and latency. So they can control this the algorithm. At the end, we add some log normal noise to this to make sure that we have the target latency all over the basically we have multiple sample of the target latency, so we can have a more accurate regression. So it's going to change the target latency, and since it's basically a low frequency, so it's going to execute less frequently than the fast loop. and it's going to control the target latency parameter for the fast loop. And here's the little bit of detail of the algorithm. Is basically capture the average throughput of the BlueStore, and it adds to the history of the target and the throughput, and then it just check the size and basically age out the oldest data. At the end, we use this history to do a regression on it and find the logarithmic function representing the curve. And we use this basically function parameters to calculate the optimal target latency, and then we add noise to the target. And all it does, it just the fast loop tries to optimize and control the throttle size, and the slow loop tries to optimize and control the target latency for the slow loop. Fast loop. And if you don't have any question, we can just jump to the code. For doing that, I have to change my screen. So most of the CoDel code is inside these two files, the BlueStore slow fast CoDel.cc and BlueStore slow fast CoDel.h. Most of functionality is here. But before going through the whole detail, I'd like to go over the entry point of this the algorithm inside the BlueStore.h and BlueStore.cc. Inside the BlueStore.h, we have just we have instance of the CoDel class, and also we had to expose the size of the throttle and the function to change the maximum size of the KB throttle on the BlueStore. So we added these lines. And in the BlueStore.cc, we have the entry points. In the constructor of the BlueStore, we are constructing our CoDel, and then we have some configs for this, which I'm going to go over it after this. And if this config changes, we are going to reset the CoDel algorithm here. And also, if the BlueStore throttle change, we have to reset the BlueStore budget as well. And here, the entry point of the whole CoDel is at this line. So when the KB, basically the transaction is done with the KB thread, after the KB thread, it submits the information about transaction, like when it entered the BlueStore and the size of the transaction. We capture the time of entrance to calculate the whole total latency of the transaction inside the BlueStore, and we capture the bytes of transaction to basically calculate the average throughput of the transaction, basically the BlueStore. So this is the only entry point of the algorithm, and basically this timestamp is getting set over here when it's basically the transaction just created and in this function queue transaction when the transaction just entered the BlueStore. In terms of configs, we have a few configs here. So the most of the configs are experimental, but the two most important config of this algorithm is BlueStore CoDel that can activate or deactivate the algorithm. By default, it is false, so it will be deactivate for now. and the BlueStore CoDel throughput latency trade-off, which is the target slope parameter of ours. This defines the trade-off between the throughput and the latency. So by applying admission control, we are going to lose throughput and decrease the latency as well. So these parameters basically keep a trade-off between the throughput and the latency. What it means, in terms of units, it means, for example, target slope of 1 means we are willing to losing at most 1 megabyte per second for every 1 millisecond decrease in the latency. So it's very straightforward and easy to set parameter. The other parameters are experimental. They are best to keep defaults. The first one is the initial target latency. So the algorithm should start with the initial target latency parameter for the fast loop. And we have the slow and fast loop intervals, how frequently they are going to be executed. By default, the slow loop is 500 milliseconds and the fast loop is 50 milliseconds. Also, we have the minimum target latency and maximum target latency to control the target latency so it doesn't go wild more than a certain value or less than a certain value. And the initial budget for the throttle is set by this parameter. And also we have a minimum budget, so it doesn't let the BlueStore throttle size decrease more than a certain point. So we are not going to lose too much throughput. And also the increment of the BlueStore throttle basically in the fast loop, when we increase the BlueStore throttle, we increase it by this amount of increment. At the end, this is the size of the history we keep for the throughput target points to do the regression on them. By default, it's 100. So I think we can just go over the BlueStore code. So on the H file, let's go over the .cc file actually. So on the constructor, it's pretty simple. You just try to read the configs and start the algorithm by calling onConfig changed. On the onConfig changed, it's reading the configuration here, and then it's trying to initialize some variable. And at the end of this function, we have two basically timer. And if I go to the .h file, I'm using the save timer in the Ceph. So basically there are two timer for fast loop and a slow loop, and they are going to execute them in certain intervals. So it just cancel all the events that already exist and just run the fast interval process and the slow interval process. In the fast interval process, which is the regular CoDel, we have a lock that basically controls the entrance of the information and also these loops. Basically, when the loops are running, the BlueStore cannot submit more requests. More transaction info to the BlueStore CoDel. It's pretty simple actually. You just check if the CoDel is activated. It's check for the latency violation, which is just a simple check. It just check the minimum latency with the target parameter, target latency, and if the violation is happening, basically it does what the algorithm does. it basically shrinks the, let's go to the minimum violation. So, so on the constructor, we have two function pointers. So there is a BlueStore budget reset callback and get KV throttle current. So these are the functions that's going to be called when the violation is happening, and basically BlueStore budget reset callback should reset and the maximum size of the throttle size, the throttle inside the BlueStore. We implemented in the function, so we don't have to pass the throttle object to the BlueStore CoDel. In the CoDel, we just call this function pointer on minimum violation. Did I pass that? Yep. So when the BlueStore budget changes, we just call that minimum violation. We just call that reset throttle size, and the throttle will be reset. And inside the BlueStore, we are basically creating this function pointer here. So they're just two Lambda functions that one of them just reset the throttle max, and the other one just get the throttle size for the BlueStore algorithm. And if we continue, so basically if the latency violation is happening or the minimum latency is bigger than the target latency, it just decreases the throttle size, and if the otherwise, it's going to increase the throttle budget size by the increment size we had in config, and at the end it's going to reset the BlueStore budget. And at the end of this code, it's going to set the timer for the fast interval amount of time, which is by default 50 milliseconds, and it's going to call this same function. So every time this function will be called in every 50 milliseconds, and it's going to call and it's going to set a timer and add the event for calling itself again. For the slow loop, we have this code. Basically, we also have the log, and if the algorithm is activated, we calculate the amount of time that for the whole interval. So to be accurate, we know that the interval is 500 milliseconds, but we measure it again to be more accurate. And then we also track over the total bytes that we accepted through the BlueStore over this slow interval. If I go to the update from transaction info, this function is called in the BlueStore, which I should show you before, and pass the transaction information to the BlueStore. In here, we track two things. The first thing is the minimum latency, and the other thing is the number of the bytes that the transaction have. We have just accumulate these bytes for the slow intervals. So at the slow interval, we can calculate the average throughput, basically. Here. So we calculate the slow interval throughput, the average, and it's megabyte per second. And at the end, we just push it to the history for the regression, and also the target latency, and we check if it reaches the maximum size of the history. We are going to erase the oldest data. After that, if the regression history reaches the certain size, we are going to use that regression to find the optimal target latency. I will go over the code for the regression after I'm finished with this function. So after finding the optimal target latency, we just make sure that it's within the bound, the minimum target latency and the maximum target latency, and then we add the basically the log normal noise. We also have a parameter to find the log normal noise parameters, and we calculate the distribution for the appropriate log normal noise, and we add the noise to the target latency at the end. And after all of this done, we reset some of the variables. Obviously, for example, the number of the bytes should be reset to 0 and some other variables. And at the end, same as the fast loop, we have we add the event to the timer to call the same function again after the slow interval amount of time. And the slope, that's the code for the slow loop. For the regression, we created this file regressionutil.h in common directory in the source. So this file contains some function for the regression and the noise distribution. So the important function here is this function that we are calling from the BlueStore CoDel. From here, it tries to find the optimal target latency based on the target slope that we are setting here. So what it does, it's do the regression on the do the regression on the regression history, basically the throughput and the target latency history that we have, and calculate basically this logarithmic function. And all we are looking for is just theta 1 or just the b constant here. And we use that to just calculate the optimal target latency based on the target slope. And for the regression, we have this function, which is a very simple and optimized function for the logarithmic regression in our case. So we use mostly matrix manipulation using the Boost library. So the details of how it calculates, it's a little complicated. I don't really understand myself, but it works. It uses the matrix manipulation, like matrix products and just traverse and other function to just calculate and find the estimation of the logarithmic function. I write the unit tests for all of these functions, so they are working pretty fine. I'll go over the unit test after this. So the regression is going to be calculated, and basically we find the optimal target latency for the CoDel algorithm. At the end, also we have the log normal distribution parameters finder. So what we want for the log normal noise is that basically our algorithm is trying to converge to a target latency after a while. But the problem is if we have to keep like a certain target latency after a while, we are going to have a very noisy and very unstable regression. For good regression, we are going to need a larger range of target latency. For example, if we have multiple points concentrated on a certain area, it's really hard to do a regression and find the exact function on them. So we add noise to the target latency so that it's going to create some higher target latency and a few lower target latency than the original and optimal target latency. So by adding this noise, we are just make sure that the regression is working correctly and accurately. And we choose the log normal because by its feature, it's favor the mode. So most the it's really probable to choose a variable really near to the mode and very less probable to find the value very high or less. So this function calculates the right parameters for the log normal distribution over a certain mode and minimum and maximum target latency. So you just convert this mode minimum and maximum to mean and standard deviation. So when we call this function, we just pass the target latency or optimal target latency as mode. So we have more variables and more values around and near to optimal target latency. And we experimented this, and it seems that by adding this kind of noise, it doesn't really mess with the throughput and the latency of the system overall. It has impacts, but it's very limited. At the end, also, we make sure that if the target latency that we choose is smaller than the optimal target latency, we just add a little bit of noise to it to favor the throughput. It randomly just increase the latency a little bit. So we don't have very low target latency, because very low target latency can affect the throughput really badly. And for the unit test, we have 2 unit tests. One of them for the whole CoDel algorithm, which is on the test files here on tests OS BlueStore slow fast CoDel. And in this test case, we just implement basically a mock of the slow fast CoDel. We set our own parameters that we are going to experiment with, and we try to control the algorithm by ourselves here. And we run basically the BlueStore CoDel on a certain basically the intervals 100 milliseconds and 400 milliseconds for the test. So we don't use the defaults here, just for the tests. And in the test case, we are going to submit some transaction information, basically the fake transaction informations, to make sure that the violation and everything is worked correctly. So we purposely add in some cases we add transactions to have the violation, and sometimes we don't have the violation. And at the end, we check to see if the CoDel algorithm could basically catch these violations. And for the regression utils, we have another unit test, which is a very simple unit test for those functions. I'm not really going to over all of them, but it's basically trying to test these mathematical functions. And yeah, that's the overall explanation and code walkthrough of the CoDel. That's all of the CoDel code. So it doesn't have a lot of interaction with BlueStore, just a few entry points, and it does all other things on itself. It doesn't need any other dependencies. And yep, I think that's it. Do you have any questions? If there's no question, I can go over the experiments results.
Thanks, Ismail. I was just going to ask about the experimental results, and after the presentation, would you mind adding the slides to your PR as well? I think it'd be very
Yeah,
helpful to reference in the future.
yeah, sure. Okay, let me go over the experiment results. So for experiments, we used generated workload using FIO. The system specs that we did our experiments, you can see it here. It has a 480 gigabyte SSD. So all of the experiments are on SSD. So we configured the BlueStore to be on SSD. And for the IO depths, we set a very high IO depths to make sure that the algorithm can handle extreme cases of buffer overload, which is 1024. And so this graph shows the target latency parameters over time. So if, as I mentioned before, the slow loop tries to change and control the target latency. And this is how it changed over time. So this is how the slow loop controls and change the target latency. For example, this experiment is 64 kilobyte writes on SSD. It starts and the times is seconds from 0 to 300 seconds. Basically, it's 5 minutes. After 100 seconds, it gets basically stable and have the basically a certain trend. It's noisy, and this noise are basically the log normal noise we add. As you can see, we have multiple range of the target latency here, from very low to very high, but mostly very close to a number, which is the optimal target latency. On the other graph, we experiment with workload change to see how the algorithm reacts. The first 300 seconds is the workload with 4 kilobyte writes, and after 300 milliseconds, it's going to change to 64 kilobyte writes. And you can see that the slow targets can easily detect that this change and change the target latency, basically fluctuation based on the workload. And the next result, this is the 4 kilobyte write on SSD. So we basically use the BlueStore without any throttles. Basically, we disable any kind of admission control, which was implemented by default. And then we tested our system with different target slope parameters. The baseline is the BlueStore without CoDel. And the other experiment you can see here, maybe I should zoom. Oops. It's different target slope. So if you remember, the target slope will define the trade-off between the throughput and the latency. So for example, target slope of 1 means we are willing to lose at maximum 1 milliseconds for decreasing the latency 1 milliseconds. And so by latency, I mean the latency of the transaction in BlueStore. If the latency of transactions decreases, it means that the transactions are not spending their time inside the BlueStore. Rather, they're in the basically in the front end. So the first graph is the throughput impacts of the algorithm, and the next graph is the latency impacts. So we have here the blue one is the average latency, the orange one is the 95th percentile, and the green one is the 99th percentile latency in the BlueStore. So you can see by increasing the target slope, we are decreasing the throughput, and we are decreasing the latency as well. So the target slope have a very good control over the trade-off. So operation team can easily decide what trade-off they really need. They might say we need a better throughput, and we don't need really latency, so we are going to choose target slope of 1 because by it's increasing it's decreasing the latency, but the throughput is not changing that much. So they might choose this option, or they can go with the other option based on their profile and their preference. In the latency, you can see that on the baseline, the most of the time of the transaction is happening in the backend in the BlueStore. By increasing the target slope, we are decreasing the latency of the transactions, and we can decrease the basically latency and keeping the throughput at the acceptable basically rate, and trade-off between the throughput and the latency. I have the same result for 64. Sorry, this was 4 kilobyte, and this is 64 kilobyte. The effect on the latency is more extreme than before. It decreases the latency by a lot, and on the other hand, it's keeping the target latency, the throughputs at acceptable rates, especially at the target slope of 1 or 0.5, and we are decreasing the latency by a lot. And these are the basically summary of all experiment that we've done. We've done multiple experiments with different workloads, but this is basically the gist of and the summary of all of the experiment and results. I have more details on slow loop, but I'm not sure if I have time. We can go over it if you have question on the details of the slow loop and how we are calculating the optimal target slope. Any question on results and so far?
May I have a couple of clarifications, please?
Yeah.
So did I get properly that you treat OSD core as a front end and BlueStore as a back end for algorithm?
Yeah, we assume the BlueStore is a backend, and in Ceph the OSD will be the front end. In the experiments, we use FIO as the front end.
And what, well, in these experiments, when you measure target latency, it was client latency, right? Or it was some operation latency measured at OSD level?
Yeah. So the latency is the BlueStore latency, is not client latency. We measure the BlueStore latency, so it means the time the transaction is spending in the BlueStore. We want to minimize this to make sure that the transaction end up in the front end instead of the back end. So we
okay, but from science perspective, there is no much difference where in which queue request is waiting at OSD level or at BlueStore one.
Physical latency, what it does is it pushes the requests up into a queue where they can have quality of service applied to them.
Sorry, Sam, I can hardly hear you.
I think, Sam, we couldn't hear you, Sam.
So, well, my question would be, what's the benefit from the client's perspective in having this algorithm at BlueStore? Would it get some trade or improvements in latency or whatever?
So basically, it doesn't improve the client latency. As you said, there's no much difference. We just moving the latency from backend to the front end. The sole purpose of this project is just increasing and improving the schedulability of the front end. And if we basically improve the schedulability, it eventually will result to a better, maybe better latency and better and fair resource sharing between users and clients. But directly, this project doesn't basically improve the latency in clients.
It's about quality of service. Can you hear me?
Yeah, we can hear you
it's
now.
better now.
Yeah, so forcing the requests up into the OSD queue means that we can apply quality of service to them. Right now, if all of the requests get slurped up by BlueStore, which is broadly true, then any quality of service we're applying at the OSD level is irrelevant because all of the latency is down in BlueStore. So
I see. Okay.
Once we've sent 10 milliseconds worth of latency down to BlueStore, any scheduling decision the OSD makes is necessarily 10 milliseconds in the future. So if a high priority IO arrives, then it's going to have a minimum latency of 10 milliseconds, even if hypothetically we could have preempted it to the front of the queue. So doing it this way means that BlueStore only consumes as much latency as it needs to hit a decent percentage of its maximum throughput, and the rest of the queue remains up in the OSD. So if one of these high priority IOs arrives, we can stick it in the front of the queue.
I see. Thanks.
Yeah, we are exploring the way to measure the impact of our work on the scheduling and quality of service. But right now, we don't have anything. So basically, we are just trying to present the results on the BlueStore latency. In the future, we are going to have a measurements on the quality of service, maybe. That how much impact we are having on the clients and the scheduling itself.
From my perspective, this is a useful first step.
Yeah.
We also already have the mClock algorithm implemented. So there is already machinery that can take advantage of this. Measurements are just future work.
Any other questions?
I'll also point out that we already do have a parameter that essentially controls this, the BlueStore throttle. So you can also view this as an attempt to auto-tune that parameter so that we don't need to figure it out anymore.
Yeah.
Did you have any information about how this handles like mixed I/O sizes?
Sorry, what?
Is there any impact of mixed I/O sizes like 4K and 4 megabyte say, mixed together in the same workload?
Yeah, we had those experiments. I didn't add them here just to have the results simplified.
Okay.
But the result was basically the same. The targeted slope was able to maintain the trade-off between the basically the workloads and the between the throughput and the latency.
Thanks.
Yeah, and the mix workload we used was like 25% 4 kilobytes, 75% 64 kilobyte, 50/50, and 75/25. If I'm not sure if I have time, go over some other slides. Is there any other questions? So I just wanted to go to more detail of how we are basically calculating why we are adding noise or why we are using the log normal noise and everything. So basically in the slow loop and calculating the optimal target latency, we just try to find the latency will result to the slope of the target slope, which is a very simple derivation. And for the log normal noise, the idea behind it was that if we have a lot of points concentrated on a certain point, we are going to have a very high value noise in the regression. So the regression will be inaccurate. But if we have well distributed points around the different values, we are going to have more accurate estimation of the regression. For example, both of these functions are random points on this function here, which is 1 plus 3 logarithm of x. But and then we create some random points based on this function, and then we try to find the regression points using our estimation. And you can see it was more accurate on the right side than the left side. So because of this, we add the log normal noise. Basically, we assume the optimal target latency is the mode, and we have a minimum and maximum. So we don't go over very high target latency, and we calculate the corresponding log normal parameters, including the mean and the standard deviation. And basically, which it does is, for example, the left side and the right side shows the change of target latency over time controlled by the slowed loop. On the left side, we don't have log normal. It is not noisy as the right side, but it is not stable. It's basically lost most of the time. But on the right side, by adding the log normal noise, we are having a very noisy change and fluctuation, but the trend and the overall value is really around the same point. I think here it was 5 or something close to it. Yep, and this is the details I wanted to share to make sure that everything is understandable. Any other questions?
All right, well, thank you so much, Ismail, for going through all this, and very interesting to see the results and how you ended up changing this in response to the data like the log normal noise, especially at the end here. I think we'll be able to follow up on the PR more effectively now, and some folks couldn't make it today, but we'll be able to watch the recording. Thank you.
Yep, thank you, everyone. Thank you for listening to my presentation.
Thank you.
Thank you.